Team, it's Mr. Z, and we're going to continue to model situations in the real world with functions. So let's dive on in. So remember, what we're doing is we're talking about sheets of metal and we're creating a drain. The sheet of metal that is originally used is 8.5 feet wide. And the idea is that we're going to take part of our region and we're going to fold the side up. And we're going to do this on both sides. And we're going to do it the same length such that it looks like a drain. Both of the sides are going to be how high this drain well is. And then this is going to be the width. Now the idea behind this is there is a connection, because you have to remember, as we were folding the paper last time, basically we could have three situations. One where we had a tiny height and a large width. And then we had another extreme where we had a super tall height but a small width. And we were talking last time about the things that are in a high quality drain. Well, you can't have it too shallow, because then the water will flood and go out in the street, causing a no-go. And the other situation is if it's too small, something can easily block the top of it, and that would cause a flood as well. So we're going to have something in between these two models is the sweet spot. Let's actually talk about math though. The height of the drain of 0 feet is asking, hey, if there is no height, the bottom of the width is going to be 8.5. If I take my sheet of metal, which is 8.5, and then now I want to fold it 1.5, this is going to be 1.5, 1.5, and I'm going to go ahead and fold an 8.5 sheet of metal, and it's going to resemble something like this. I have to figure out, well, what the heck is going to be the new width? Pause, take a moment and think about this. How would you figure out this region when you know this region? Think of it as an equation. 1.5 plus something plus 1.5 is 8.5. This becomes 3 plus x equals 8.5. X is going to become 5.5 by subtracting 3 from both sides. So what we're going to do here is we know it's going to be 5.5. Notice the process. To do 3, I want it to be 3 feet on the side. And if I started with 8.5, 3 plus something plus 3 is equal to the original size of the metal. This is going to result in a piece that is 2.5. Notice, as the height of the drain increases, the width gets smaller. That's true. Look at this picture. As the height increases, as it goes from a small height to a large height, the width will decrease. We see that modeled. Now, a general rule for this is my height. What do I have to do with the height to get the width? Can I write up some sort of equation? Well, I know that it's going to be 8.5 minus 2 times the height, and then this is going to be equal to the width. 8.5 minus 2 times the height. So go ahead. I want you to fill out this table. I'm going to give you some values. And then go ahead, play around, pause the video, and then unpause when you have determined the bottom width for each of those. And they are as follows: 7.5, 6, 5, 3.5, 2, and then 5. What about this guy? I saved it last on purpose. So what I want you to understand about this next one is it's easier to see what happens when I try to draw a picture for the situation. I'm trying to model it. So I have something that's 8.5, and I'm going to fold the sides to be 5 and 5. What is going to be left? But if I fold 5 and 5 make 10, that's going to be more than what we have. So this is impossible. Again, if I were to plug it into this equation, W would be a negative value. Can height be negative? No. So there is no drain that is created because I cannot physically create a drain with 8.5 worth of material. Okay, so the engineer needs to identify measurements that allow the most water to flow through the drain. So what does the engineer need to calculate? What does she need to consider? The first being is that they need to the drain cannot be too small, otherwise it gets clogged. 2, the drain has to be tall enough to prevent flooding. Okay, let's talk about this more. So when we're getting to the nitty-gritty of math, even though the top is hollow, it does create, based on the height and the bottom width, a rectangle. This is called the cross-sectional area, and this is what we're going to be diving into. The cross-sectional area is a rectangle. The area of a rectangle is always base times height. Describe how to determine the cross-sectional area of any drain. So just remember, when we bent the metal, we created a rectangle. So you're going to have to do the cross-section area. It's equal to the bottom width times the height. So predict and describe the drain with the maximal cross-sectional area. Well, let's go ahead and just look with predicting our data from the last page. So the maximal cross-sectional area. What we would need to do is we would multiply all of these together. We would multiply 0 times 8.5, 0.5 times 7.5, 1.25 times 6, 1.5 times 5.5, 1.75 times 5, 2.5 times 3.5, 3 times 2.5, and 3.25 times 2. I am multiplying the base times the height to get the area, and I would look at which one is the greatest. That sounds like too much work. You can do it. That's how you have the tools before. So the idea is that to describe the maximal cross-sectional area, a maximum, we want the largest sewer drain, essentially, possible. Or not, yeah. So what could we do? We need it big enough and we need it tall enough to prevent flooding. So let's go ahead and figure out a way to get what this maximum has to be. There has to be an easier way. Well, we're going to have to take the height times the bottom width, right? We're going the area of my cross section is equal to base times height. The area of my rectangle is equal to the base, which is the bottom width. So the bottom width times height. Wasn't there a way I figured out how to find the bottom width? Wasn't the width equal to 8.5 minus 2h? I'm going to use this value for the bottom width times my height. Well, that was just h. I'm going to clean this up so that algebraically, this is going to be the area of the sky is going to be h times 8.5 minus 2h. Notice I modeled this situation. I need to find the maximum. I'm going to hit a pause on that. We created a rule. Now, the only difference in this rule is it wants you to use A of h. The area for when h is the value. The area when h is equal to h times 8.5 minus 2h.